In a previous video, we described a situation where a company was producing batteries that were supposed to have a mean charge of 2.4 volts. And a question came up about the manufacturing process as to whether or not these batteries were actually carrying a capacity of 2.4 volts. So what we're going to do then is use what we know about the normal distribution and what happens when sample sizes are at least 30. So in this case, we have a sample size of 50. We know that the sampling distribution would be normal. And the question then is the sample mean for this type of battery equal to 2.4 volts? So in other words, is this the actual distribution here? A normal shaped distribution, because again, our sample size is at least 30, with a population mean, right in the middle here, of 2.4 volts. We've talked about that we would use the fact that it would be extremely unlikely that we would land way out in the tails if the mean is 2.4 volts. And if we do land way out in the tails, then we would reject that assumption that the mean is 2.4 volts. But what we need is an organized process for doing this. And that organized process is going to be called hypothesis testing. And when we conduct a hypothesis test, we're going to start with what we call a null hypothesis. And the null hypothesis, we're going to symbolize using this H and then a subscript 0, the null hypothesis. And that null hypothesis is this assumption here, this assumption that the mean is 2.4 volts. Again, we would reject that assumption if we land out here in these tails. Now, if we're going to reject that assumption, then there must be some alternative conclusion. And that alternative conclusion we're going to call the alternative hypothesis. And we symbolize that with this capital H with a subscript of 1. Sometimes you're going to see a capital H with the subscript of A. I'll just kind of put those over here. Sometimes it would be H sub 0 and H sub A. But it's the same thing. It's the null hypothesis and the alternative hypothesis. Here we're using a 0 and a 1. And what is that alternative? If we reject this assumption that the mean is equal to 2.4 volts, then the only thing left for us to conclude is that the mean is not 2.4 volts. And way up here to the right or way down here to the left in these unlikely areas would cause us to reject that the mean is equal to 2.4 and conclude that it's not equal to 2.4. So our hypothesis testing process starts with these hypotheses, the null hypothesis and the alternative hypothesis. Now, once we've done that, then we need to establish some things about this particular hypothesized distribution. So out here in the tails, we have what we were calling the unlikely area. And we talked about how if an event has a probability of no more than 5%, then we would consider it unlikely. So what we're going to do is we're going to let alpha be 0.05 this time. And if we split that out into two tails, then alpha over 2 would be 0.025. So we would have 0.025 out in each one of these tails. And from this curve then, we can see that if we land in one of these tails, then we would reject this assumption that the mean is 2.4 volts, and we're going to have some way of determining whether or not we've landed in those tails. And we will do that initially by looking at some what we call critical values. And so we'll abbreviate that as T crit. We're using the T distribution because we do not know the population standard deviation. So we're using the T distribution for these probabilities. So we need this critical T value. And we can use a table, or we can use StatCrunch, or we can use the TI-84 calculator, or any other means available to us to find these critical t-values. First, let's use StatCrunch to find this critical t-value. We'll click Stat, Calculators, T. The number of degrees of freedom is 49. Now, what goes in this box is the actual t-value itself. What goes in this box is the area that is accumulated up to some t-value. So what we will do then is we'll type in 0.975 here, because that leaves us with 0.025 out in the right-hand tail, just as we have on our picture. Now click Compute, and now this looks like the picture that we drew a second ago, except for that left tail doesn't show, but that's all right, because the t-distribution is symmetrical. So all we really need is this t-value here, which, when we round it to 3 decimal places, would be 2.010. Now let's look at a t-table. Across the top here, we have those areas that we talked about a second ago and that we saw on that picture. This area here, 0.975. So across the top we have those accumulated areas, or accumulated probabilities. And then on the far left we have the number of degrees of freedom. So let's notice that this third column over gives us this area of 0.975, and then let's drop down to where we have 49 degrees of freedom. And we see that in that third column, we find that 2.010 number that we found when we used StatCrunch. If we want to use the TI-84 calculator to find this critical t-value, what we would do is push second, variables, distribution, and we want to use this inverse t function. So we'll hit 4. And the area out to the left of that right critical point would be 0.975 if we take alpha, split it out into 2 sides, and have 0.025 in each tail. The degrees of freedom for a test with a sample size of 50 would be 49. So we'll hit paste, and then for those who are using a TI-83 or 84 calculator that doesn't have that nice little menu of where to put things, this would be the syntax. You'd use that inverse t function, and then you'd put the area first, that cumulative area, then the number of degrees of freedom, 49, and hit enter. And it's going to give you this number 2.010. So we found that in this case, the critical t-value is 2.010. And since this thing is symmetric, then we would have a critical value of 2.010 to the right and a critical value of minus 2.010 to the left. Now we're going to calculate what we call a t-test value. And that t-test value will be found using this formula, x bar minus mu over s over the square root of n. And what we can see then is that if that t-test value is greater than 2.010, or if that t-test value is less than minus 2.010, we would reject this null hypothesis, because we would be saying, well, this assumption just probably is not right, because it's very unlikely that we would land in these areas down here. And if our test value associated with our sample mean lands in these areas, then we would not believe that the mean is 2.4. We would believe that it's not 2.4. And in calculating this, then, we find 2.35 minus 2.4 divided by 0.2 divided by the square root of 50. And we're going to find that to be minus 1.768 if we round to 3 decimal places as we did with our critical value. We can use the calculator to do this, or we can use StatCrunch. In order to use StatCrunch to find this, we'll click Stat, T-Stats, one sample with summary. The sample mean was 2.35. The sample standard deviation was 0.2. The sample size is 50. And the null hypothesis was that the population mean was 2.4. We have a little drop-down box here that allows us to do either a two-tailed test like we have going here when we are judging whether or not it is equal or not equal. But we could also be doing a test where we might be asked to make a judgment about whether or not a population parameter is less than or greater than some value. So we'll click Compute. And again, we find this minus 1.768 value if we round to 3 decimal places. Now, we have this, our null hypotheses. We have our critical values, which we used in this little decision rule here. So we'll call that a decision rule. Then we have our test value, which we have calculated. And let's remember for a second how we got these values. This one we looked up. We looked it up. So we look up our critical value. This one we calculated. So we will calculate the test value. Now, where did this land? Well, it landed in here. And we decided that only if we landed out in these tails would we reject that this population mean is 2.4 volts. So what's our conclusion going to be? Again, we have to keep in mind that we cannot prove anything using a sample. The only thing we can do is make a determination about whether or not something is particularly unlikely, in which case we would reject a hypothesis. Now this time, we're not going to reject this hypothesis. The evidence that we gathered did not lead us to reject that the population mean is 2.4. So we need to come up with some sort of a conclusion. And that conclusion should say something about the evidence that we gathered. So these measures that came from this sample of 50. It should also refer to the fact that we have a particular level of significance here, this time 0.05. And it should refer to our hypothesized mean here, or our assumption. So we might say something like sufficient evidence was not gathered at the 0.05 level of significance to lead us to conclude that the mean is different from 2.4 volts. We might also make the statement that we should not reject the null hypothesis.